Hi everyone, I'm Julia Hyder, Senior Editor with Modern Machine Shop, and I'm your moderator for today's webinar, which is sponsored by SolidCAM. We'll cover how iMachining can improve the performance of any CNC machine with any cutting tool by reducing programming and machining time, and how the iMachining Technology Wizard feature can automatically provide optimal feeds and speeds to ensure success on the first part. Our presenter is Ken Merritt, Director of Special CAM Projects at SolidCAM. Recognized as an accomplished CAM programmer, Ken brings technical capability, product innovation, and training and support skills. As a CNC trainer and product manager with extensive knowledge of how technology is best leveraged in the workplace, Ken's background and skill set is aimed at making SolidCAM customers more successful and more profitable. You can submit questions for our presenter at any time during the presentation using the Q&A tab on the right, and we'll answer as many as we can at the end. I also wanted to let everyone know that this webinar is being recorded and attendees will receive a link to the recording via email. So with all of that, let's get the presentation started.
Okay, well, thank you, everybody. I appreciate you being here today. And we're going to talk about iMachining, both 2D and 3D, and how it can help your shop be more productive. So I'm going to go ahead and turn my camera off for the presentation. When we get to the Q&A, I'll come back in and we'll go there. All right, so as we begin to talk about iMachining is part of the SolidCAM suite of modules that are very productive. SolidCAM is really a full-featured program. We do CAM inside of SolidWorks, Inventor, and Solid Edge, and then we also have the iMachining module is integrated into NXCAM. So we have iMachining for NX. Now, we do everything in our software from simple 2.5 axis machining all the way through the most complex 5-axis simultaneous and into the very, very sophisticated machines like the advanced mill turn and the very advanced Swiss turn machines. SolidCAM presents many technologies that give us the ability to really manage toolpath at a higher level. For instance, we can manage everything up to unlimited numbers of channels of synchronization, and we can also handle an unlimited number of axes of motion. We can do up to 5 simultaneous, but what's really kind of interesting, we can actually do 5 simultaneous on 2 independent channels simultaneously. So wrap your head around that one. That gets pretty complex. But today we're going to be talking about the iMachining 2D and iMachining 3D modules. And so let's go ahead and get started on those, and we'll take you directly into that. Now, the idea of launching your productivity with iMachining 2D, iMachining 2D is a bulk material roughing module. It's absolutely the best way to remove material. It has feature recognition for geometry selections. It can also, of course, do the simple chaining that we've done for years and years. And it is also accessible in 3+2. So if you're on a 5-axis machine and you want to orient the part to another side and continue machining on that, iMachining 2D will support that as well. There's a number of types of parts that we work with that are really kind of made for iMachining. Of course, your 2-axis prismatic parts and 3-axis mold cavity parts, but a lot of people don't think about the 5-axis like impellers and such. With the 3+2, we can use iMachining in those cases to rough out those area between the vane segments. Same thing with like screw machining and such. We can go to different indexed orientations and rough out that material. Now, in a lot of cases, the iMachining for 3D is a very powerful utility for that because it gives us the ability to look at updated stock. And we'll be talking about that a little bit later in the presentation today. Now, there's a lot of things that we do with iMachining, but the automation strategy of it is to take information from the material, which we get the ultimate tensile strength, machinability. We can assign minimum and maximum cutting angles to a particular material. The tool, where we get the cut length, we get the number of flutes, we get the helical angle of the flute, okay? And of course, we can assign the chip thickness. Now, chip thickness is an interesting parameter. We'll talk about that in more detail later, but this is not the chip load at the front of the tool. This is chip thickness at the actual cutting angle. Also, the grade of the material of the tool can have an impact on how we want to machine with iMachining. With the geometry, we're looking at not only the shape of the geometry, but the depth of the geometry also. We do the updated stock that I was talking about. That gives us the ability to optimize and reduce very dramatically or even eliminate any unwanted air cutting. Then we also take into account the machine kinematics. Now with the machine kinematics, we're looking at things like the maximum spin of the spindle, the maximum feed rate that the machine can drive on contour, okay? What is the maximum horsepower? Because this is a force-based calculation, and we're going to want to get into some details on that here in just a moment. We're also interested in the rigidity of the machine. Now, the beauty of all of this is the iMachining wizard takes into account all of these different parameters and brings them together in equations that allow it to set up all the different cutting parameters that we need for iMachining to run so that you as a user don't have to try to figure that out. The wizard does that for you. Now, iMachining is based on the tool cutting angle. And this is where it gets very important to understand the physics behind this. Now, as you see on the left, the pi segment is 55 degrees. Over on the right-hand side here, we're looking at a 150-degree pi segment. Now, there's some interesting issues that occur when we go past that 90-degree quadrant. And that's one of the reasons why iMachining doesn't do that. We operate with what we call an advanced morphing spiral. It is actually a very intelligent toolpath, and it allows us to range between 10 degrees and 80 degrees in order to manage morphing from one shape to another shape while keeping the tool in contact and giving us a more effective toolpath that is continuously removing chips as much as possible. Okay. This is what a morphing spiral might look like depending on the shape that we're dealing with. And as you can see, it is kind of an interesting looking toolpath. It's a little bit variable in certain areas, but it is a continuous toolpath whenever it's possible. Now, by taking the wizard and incorporating the tool material, machine, and geometry information that we were talking about earlier, our wizard can really give you very, very strong capabilities without you having to figure out how to blend them all together. Okay. Now, as we start talking deeper into the system and we really look at what's going on, we also want to look at things like the vibrational functions, and we want to control the cutting angle so that we don't generate vibration. Now, we do that by controlling the step over. Now, most people are used to using language like step over. I prefer to think about the cutting angle. Now, step over on one size tool is completely different from the same step over on another size tool. You take a 1/4-inch tool with a 45-degree step over or 45-degree cutting angle. That radial step over is going to be completely different than if you're on a 1/2-inch tool with a 45-degree cutting angle. So one of the things that we do is we ensure that the tool is never over engaged. We're going to make sure as we're working through this spiral, the morphing spiral, that we never over engage that tool. It's always safe. It's always protected. We're going to control those cutting angles. Now, there's a lot more involved in this than what most people understand or think. This has to do with managing the cutting angle in concert with that chip thickness that we talked about. We're going to control how we approach and depart from particular areas within the cut. And we're going to do that with very sophisticated algorithms that ensure that we're not taking an invalid step that would either over-engage the tool or that might snag on the breakthrough and cause a breakage of the tool. All of this helps us to minimize the forces that apply to thin walls and thin floors, and it gives us a much better functionality when we're cutting for maintaining non-warped parts when we're finished. And we'll talk about that again a little bit later on in the webinar. The beauty of it is that all of these parameters are automatically calculated. The user doesn't have to worry about trying to figure out how to do this on a calculator. The wizard handles that for them. Now, the way a morphing spiral toolpath works is, number one, there are no sharp corners. It's always tangent. So as you can see it beginning to move the material out of here, the morphing spiral allows it to change from one shape to another. Now, in this case, we're showing the morphing spiral combined with what we call D-slot trochoidal repositioning moves. These are fast repositioning moves that keep the tool down and don't waste time going back and forth between G1 and G0. And again, the most important aspect of this is that the tool is never over-engaged. So as we look at this in a closed pocket, let's take a look at how this works. Number one, we're going to do a helical approach to get into the depth. Then it's going to generate the first morphing spiral. This is, again, changing from one shape to another shape and keeping the tool engaged in the cut the entire time. This is a very important feature of SolidCAM's iMachining. The next thing it does is it begins to blend the shape to bring it back into the cutting angles where it can go back into morphing spiral. It's very, very important, because when we specify the range of angles that we want it to cut from, we want to make sure that that morphing spiral remains within those angles as long as it can. The D-slot trochoidal repositioning gives us the ability to open that shape up into another area where the tool can then go back into the morphing spiral and change again from that shape into a completely different shape. Again, keeping the tool engaged as much as possible so that we're really being efficient and effective with the chip removal. Now, once we've done as much of that as we can within a particular area, then we have to get into the corner clearing. And this is where the D-slot repositioning of the morphing spirals will clear the corners out, nibbling them into a closer alignment with the actual geometry of the pocket shape, while still never overloading or over engaging that tool. Very, very important. Now, in order to do that, sometimes we're going to have to separate an area from a wall. Okay, a morphing spiral, especially a continuous morphing spiral, is the most effective material removal path that can be done as long as it is done right. Now, there's something interesting about a long, narrow area. Now, if we try to collapse from this area to the center, and of course from this area to the center, at the same time that we're collapsing from here to the center and from here to the center, then obviously we would have to use different types of step overs to do that. And so in a situation like this, one single continuous morph would wind up being rather inefficient, because along the long sides, it would be cutting it very near the minimum cutting angle and just barely taking any material off at all. Of course, across those short sides, we would be closer to or at the maximum cutting angle, where material removal rate is extremely efficient. And this would give us an interesting tool path, because we have an awful lot of the long sides at minimum, and it wouldn't really be as efficient as we would like to see it. So what the algorithm does is it automatically computes where to put these, what we call spiral efficiency separation channels, and clear those areas into more symmetric regions where we can assign the final spirals and keep them closer to or at the maximum cutting angle where the efficiency is the highest. This is one of the really interesting features of the algorithm, and it does this all automatically for you. Now, iMachining 3D brings us into a whole nother realm of things that we want to talk about and things that we want to get into. iMachining 3D is designed to use full model recognition. So instead of picking out chains and identifying areas that we want to work in iMachining 3D, it simply looks at the entire model and figures out how to machine it quickly. Okay. It also does what we call automatic stock update. Now, this is a very powerful feature, and you'll kind of see how that comes into play here in a little bit, but it gives us the ability to make sure that we are not ever wasting time with our tool just cutting in the air. Okay, so it eliminates those air cuts for us. It also does scallop calculations. Now, this is a very interesting aspect of it because in a lot of cases, the traditional way of doing a roughing and finishing is to rough it all out with flat tool paths, then come back in and use quite often a larger ball mill with really aggressive large stepovers and kind of semi-finish everything to break down the staircases that were left by the roughing operation. Well, with iMachining, the scallop calculations allow us to assign what we want those staircases to be, and you can actually bring the model into a near net finish condition very quickly and very effectively with the roughing operation. And in many cases, eliminating the need for that secondary semi-finishing operation that actually takes quite a bit of time to do. So let's take a look at how this works. The iMachining and algorithms in Wizard are operating in the same manner and fashion as they were in 2D, but they're based on the 3D toolpaths in this case, or the 3D shape of the model. In many cases, not always, but in many cases, we can rough out the entire part in a single operation. It does rest roughing functionality, automatically picking out smaller corners with smaller tools. It also makes it extremely easy to rough out very complex parts, things that if we had to set up constraint boundaries might be very complex to figure out where to set the constraint boundaries. With iMachining 3D, the system takes care of that for you. This is great for roughing with solid cutters. Many people don't realize it's also very good for roughing with inserted cutters, and we'll talk about that in a little bit as well. We use what we call a step-up technology driven by the shape. Now, the idea with this is iMachining is going to allow us to take a much deeper depth of cut in the initial roughing operation. And so we're going to take it from that point and begin working our way up the model, reducing the staircases as we go and creating that near net surface finish. This gives us less retracts, less air cutting, and, as I said before, the opportunity in many cases to completely eliminate a semi-finishing operation. This is kind of how it works if you want to watch this through. So we took the deep roughing pass, then we're coming back and staircasing it up, and then we can go back to our rest materialing. So as you can see, this is a fairly coarse strategy here. But now we come in with another operation and we begin to reduce each of those individual staircases even more, getting that smaller tool in tighter to those internal corners where the bigger tool didn't fit all the way in. And we have two things going on at once. We're continuing that roughing process, we're clearing out the smaller corners, and of course, we're also creating that near net finish. Now, let's go kind of through the feature summary here and talk just a little bit, reiteration about what we're looking at. We do trachoidal, spiral, and smooth tangent toolpaths. We integrate that with minimum retracts, and we really drop down the amount of air cutting because we know exactly where the stock is. We generally get to use up to the whole cutting length of the tool. This is pretty important. In a traditional toolpath, standard pocketing operation, generally we're just using a very small portion of the end of the tool, wearing that out, and the whole rest of the tool is still sharp. With iMachining, because of how we're managing the force loads, we can use the entire tool in many cases and get to utilize all that sharp flute that we don't use in the other way. The other thing that's really interesting about iMachining is very gentle on small diameters of tools as well as very thin walls. Now, the reason for that is the fact that we're based on physics. We're actually doing force load based calculations, and we can get into that to talk more in detail about that as well. This produces a lot less vibration because the tool and the material are never seeing what we call a linear force vector. They're only seeing rotary torsional force vectors. And so the vibration is significantly reduced automatically. This increases our tool life, and we'll show some other things about this that really are very important. I got a video I'm going to show you in a moment that really shows how high a performance we can do, and yet we get significantly longer tool life. Because of all the reduced vibration, because of the reduction in the linear force vectors against the machine, a nice added benefit to this is that we're also increasing the spindle life because we're not creating vibrations on the bearings, we're not forcing loads on the ways, we're just treating the machine very nice. Now, this obviously shortens the cutting time. And of course, the marketing language is, up to 70% reduction and more. And that's very true. In many cases, believe it or not, it's even significantly higher than that. We have seen tool paths reduced from hours to literally minutes in many cases, even in complex materials or exotic materials that are generally seen as being very, very difficult to machine. Another benefit of all this is because of the way all the physics lines up, it creates very good chip ejection. We're not running into chip compaction because we're not pushing the chip into the direction that we're moving the tool. And so this gives us great heat dissipation and minimizes the amount of thermal warpage that's created as well. Now, just recently, in fact, last week, we were at the Westech show out in Long Beach, California. This is our little demonstration machine that we do. It's built for us by LaVille. It's a small desktop machine. We can get in and out of the trade shows very effectively. But this gives us some amazing ability to present our iMachining technology to the world and let them see exactly what this can do. So let's take a look at this video. Now, this is actually cut in 17.4 pH stainless steel. Now, pH stands for precipitation hardening. This material typically is in the low 30s in a preheat treated condition. But if you work harden it by heating it up, you can take it up into the 42 Rockwell C range very easily. Notice we're cutting this dry. This is a 3/16 inch tool, and we're cutting it 3/8 of an inch deep. And we're doing this right now at 18,000 RPM and over 200 inches a minute in a 45-degree cutting angle. Now, what's really amazing about this, you can see all the chips building up outside this. I don't know whether you can hear the sound of this video or not through this presentation, but we can make this video available for you so that you can hear it. It is a very, very stable sound. The sound does not change in frequency when it's in cut. It doesn't change in tone, and it doesn't change in volume. Now, the reason we can do that is because with each movement of this in this morphing spiral that you're seeing here, as the cutting angle is ranging between minimum and maximum, we are also modulating the feed rate so that the chip thickness at the actual cutting angle remains constant. Therefore, the force load on the tool, on the material, and on the machine also remains absolutely constant. It's a very, very powerful way of doing cutting. And as you can see, we're not wearing this tool out. We're not hurting this tool. This is extreme performance on a 3 horsepower spindle on a desktop CNC mill. And we're cutting it over 2 times diameter depth of cut on this tool in a material that most people would never consider cutting dry because of that thermal characteristic. And yet we're able to do it with iMachining. We're able to do it very fast, very effectively. And something unique you're about to see here is when this is finished, I actually reach inside the machine and grab a hold of that tool, and that tool is room temperature. It's not even warm. The part is not even warm. And so this gives us a great ability to do extreme performance machining while protecting the tool. Believe it or not, all of those chips you see in that machine, were cut by one tool at the performance rate that you just saw. So it's absolutely amazing what we can do with iMachining in protecting the tool, protecting the machine, protecting the part, and yet getting extreme performance in doing that. So let's go back over another area that what iMachining can do. What if we're dealing with exotic materials? Okay, this is jet engine hot section material. This is some of the toughest material you will see in the world. It's designed to have an extreme, what they call creep rupture strength, where it can stand up to extreme pressure at highly elevated temperatures like the internals of a jet engine. Okay. In doing this, we're actually doing this cut. This is a material called Rene 65. This is a GE proprietary material that is very, very difficult to cut. The tools that you see there in the picture are actually ceramic end mills. Now, ceramic end mills give us much better tool life in this exotic material, but you have to be very, very careful how you use them. If you shock that tool at all, you'll cause it to crash. You'll destroy the tool. But if we can feed it in and out very, very smoothly, and we can never overload it at all, and we can keep the force load on it very, very constant, that tool will last an amazing amount of time cutting a very difficult material. Now, in this video, we're actually cutting almost 10 times deeper than anybody's ever cut with carbide tooling at about 2.5 to 3 times faster than they do with carbide tooling or any other program. And we're getting about 3 to 4 times the tool life of what they would get in the other performance ranges with a carbide tool. So this gives us a really interesting ability. iMachining actually gives us a parameter called the entry rate. The entry rate allows us to change how the tool is going into and out of the cut. In a carbide tool, we want to get in right away. We want to get that tool in, get it under the chip, and get it cutting. In a ceramic end mill, it's exactly the opposite. We got to come in extremely gently, bring it in nice and smooth, and gradually increase its engagement, or we'll shock that tool and destroy it. So iMachining gives us the ability to handle that. Now, this is another example, and this is in a heat-treated steel. Okay. Now, this is Greenleaf ceramic end mills, and this is cutting in 52 Rockwell C material. Okay. And notice that it is just peeling material out like crazy. The sparks are normal. It's kind of cool watching this with the lights out. It really makes it interesting. But when done correctly, even in hardened materials using exotic tools, iMachining can give you extreme performance and improve tool life while at the same time protecting your machine and protecting your material, your part, and protecting the tool. Now, this is an interesting cut here, something that a lot of people never think about. This particular tool path, this is in a Duracast material, and this is using a high feed mill. It has triangle inserts. This is an 1.5-inch tool with 3 inserts. Normally, this tool is run at 500 RPM. This tool is run at about 40 inches a minute at 80% diameter tool engagement. And it makes so much noise and stresses the machine out so bad that it's just brutal. In this particular case, I'm running twice the depth of cut that they recommend, but I'm using an iMachining methodology. I'm only running at 50 degrees cutting angle. I'm running at 4,300 RPM and almost 600 inches a minute, about 550 inches a minute. The normal way, the spindle load meter was over 90%. In running this, the maximum it went to is 57%. So again, very, very powerful control over the tool and changing the game, even working with inserted cutters. Now, when we start talking about big aircraft parts like this, bulkheads and such, one of the biggest problems that we have in machining these things is the work-induced stress that we impart to that material as we're machining it. And so in traditional machining, this part would go through a whole machining scenario, remove about 95% of the base material to get to the finished part. And then when you unbolt it from the fixture, it warps like a potato chip. Well, iMachining can reduce that, significantly reduce it, and then sometimes even eliminate it. Because again, we're not putting any linear force into the part. We're not creating any heat-induced stress into the part. And so, therefore, when we get done machining this and we unbolt it from the fixture, it remains almost completely neutral. And we have much less post-machining processing to do to get this part ready for assembly. Okay, so a quick little recap here. Increased performance with iMachining, reduced cycle times, sometimes dramatically reduced cycle times, extended tool life. This is really important because your tooling cost per part can come down substantially. Best in the industry with exotic materials. There's nobody else that can challenge what we can do when we're cutting exotic materials. So best in the industry with the exotic tools. When we're using these ceramic end mills or these complex feed mills, we can take advantage of iMachining's scientific algorithms to drive those tools at a highest performance level. And we can even get into noise abatement. That part that we showed in the Duracast cast iron, that ran in the shop so loud that you had to have earmuffs and earplugs in when they did it the traditional way. When I ran that part with iMachining, not only did we cut that part faster at significantly higher spindle speed and feed rates and depths of cut, but the noise was about a third of what it was running the traditional way. So this even helped that company out with OSHA compliance. Okay, so some really interesting things, so many side benefits when using iMachining. Eliminating and minimizing stress-induced warpage. The amount of money that can save a manufacturer in the long run is absolutely stunning. So think about iMachining and think about what it can do. It can increase your productivity, increase the life of your tools and your machines. If we're not creating all the stress on the machine, the spindle bearings are going to last longer, servo drives are going to last longer, everything. Here's the bottom line. Every minute that you're not using iMachining, you're losing money. So we hope you've enjoyed this. And again, some more things to think about. Kind of a famous quote from Peter Drucker, the best way to predict the future is create it yourself. You can do that by taking on the challenge of using iMachining for your material roughing processes. Well, I want to thank you for joining me today, and that leaves us a little bit of time now for Q&A. So we'll go ahead and open it up for the questions and answers.
Thanks, Ken. It looks like we have a couple questions already, but there's still time to submit one. You can do that using the Q&A tab at the right of your screen, and we'll do our best to get to it. If we don't get to it today, someone can follow up with you via email.
Okay, great.
All right, first question. What are the main differences between iMachining 3D and iMachining 2D?
Good question. The iMachining 2D is based on prismatic geometry. Okay, and so essentially that's going to be pockets and external profiles and things like that based on the stock definition. The iMachining 3D takes into account the entire shape of the model, especially when we get into like complex mold cavity and core type models. It gives us the ability to, in a single toolpath, without even having to pick anything, it automatically recognizes the entire model, and it does that machining, including scallop calculations, all automatically on that 3D model. Very powerful add-on feature.
All right. How is iMachining different from other high-efficiency machining tool paths?
Again, that's a great question because there's a lot of competitors out there that claim to have something very similar to what we do with iMachining. In fact, when you look at their toolpath to an untrained eye, they do look very similar in the toolpath. But nobody in the industry is using what we call our morphing spiral. This is a patented feature in SolidCAM's iMachining. We actually have 7 patents on iMachining technology that nobody else can do. There are several things that really separate us from everybody else in the industry. Number one, because of the way that we are calculating the engagement angle, the cutting angle, if you will, and because of how we're managing the morphing spiral, ranging that angle from a minimum to a maximum all the time so that that spiral can morph from one shape to another, we are managing the feed rate simultaneous with all of that so that at the actual cutting angle, the chip thickness never varies. It's amazing. That picture I showed of the tool bed with all the chips in it, you can literally take a micrometer and go pick up a chip from anywhere and measure it, and you're going to be within 1 or 2 tenths on the thickness of that chip. It's absolutely stunning how consistent it actually is. And that's because of many of these patented features that we have in iMachining. Nobody else can do that. They work on step over, they work on, in some cases, cutting angle, but a single cutting angle. And they just don't manage the physics of the cut the way we do. Because of how we do that, the force vector that is applied to the flute of that tool, even at that very, very sharp edge of the flute where it's cutting, the most delicate part of that carbide substrate, that force vector ensures that the force that that tool is going to see is only compressive force. That carbide substrate is not seeing tensile force. So we resist microchipping much, much longer than any other software in the world.
All right. Can iMachining estimate tool life?
Not yet. We are beginning to work on several ideas, including acceleration, deceleration. We're beginning to start to take a little bit of a deeper physics dive into just analyzing the interaction of the tool and the material. So at some time in the future, it might be able to. One of the things that we can say at this point is iMachining will give you a very consistent tool life. So once you start cutting with it and you determine what that tool life is in the particular conditions that you're dealing with, you can count on that to be very consistent. Like I said, in that one picture, we cut all of those chips in the bed of that machine with one tool. And we do that at every single trade show that we go to. In fact, one of the things we were showing at this particular trade show, we had a tool that we used at the last trade show where we cut over 138 pockets with that one tool, and you can't even tell it's a used tool. So no, we don't predict what the tool life will be, but we maintain that tool life within a very, very close ratio every time.
All right. How does the usability compare to MasterCam?
That's a kind of a personal question for different people. Everybody has their own ideas on usability. One of the things that I really like about the way we do it is that we do a lot of the calculation for you. So instead of having to figure out what step over and what feed and speed I'm going to run at and why relative to the material, all I really need to do in using iMachining is simply input to the material database what the ultimate tensile strength is and its machinability factor. And if I want to get more specific, what cutting angles I want to use, and then tell it what tool I've got, what's the diameter, what's the helical angle, how many flutes has it got, what material is it, tell it what my machine is capable of doing. Very simple. It's got a 30 horsepower spindle. It runs at a maximum of, say, 18,000 RPM or something. It's very rigid or it's not very rigid. Tell the system that. And the iMachining wizard will automatically calculate 8 individual parameter sets running from a very conservative toolpath to a very aggressive toolpath that I can use. And I love the way Kevin says this. In fact, Kevin, are you you still listening to us? Can you open your mic? He may not be able to open his mic today, but Kevin always says this. He says, with level 1, I can put it down on sticky tape on the table. With level 8, I'm going to lock that bad boy in a vise and hang on to it good. Okay, so the level 1 to level 8 is giving me ranges of performance, but I don't have to think about what to do with those parameters. The wizard takes care of that for me and gives me first part cut success every time.
All right. Is the Solid Edge integration available yet?
Yes, it is. It is. And we are starting to roll it out. We've already got a couple people using it. In fact, I'm going somewhere tomorrow to do some training with it. So it's pretty cool. It does work.
Awesome. Is this available as a plugin to other CAM systems?
Yeah, one of the things that we really are excited about, this is also available as iMachining for NX. So when we look at a lot of these exotic material companies that we were talking about, like the GE proprietary materials for jet engine hot sections, most of those companies actually use NX. And it's kind of the standard of the industry out there. So we made a plug-in for iMachining to plug it in directly to NX so that you can now use our iMachining technology within the NX CAM system.
All right. I am not a current SolidCAM user. Is iMachining included standard with SolidCAM, or is it an option for an additional cost?
Well, it's an interesting question, but we break everything out into modules. So if you're buying our 2.5 axis standard, no, then it's an additional cost. If you're buying our 2D Pro, then 2D iMachining comes with that. Same thing with our 3D standard package. We have a reduced cost 3D standard package that we make available to people. It does not include some of the higher performance 3D toolpaths, nor does it include the iMachining 3D. The 3D Pro toolpath or module that we sell includes both the high performance 3D toolpaths as well as the iMachining 3D.
Okay. When I use SolidWorks to create a part with a ball head and the part has a very small angle, it leaves a lot of rough-like material on the part. How can I avoid that using iMachining, or is it possible to use a variable step over?
I missed the first part of that. With a bald head?
Ball head.
Okay, I thought somebody was maybe looking at my camera picture. Yes, I have one of those. The idea of roughing with a ball tool is something that's been done in the industry significantly for many, many years. It's not something that I tend to like to do, because at the center of the ball, you're not getting a very high rotational velocity. And so as you're trying to rough out a bunch of material with that ball cutter, you're down at the center of the nose, you're effectively dragging a piece of carbide, kind of like broaching across your material. One of the things that I feel is better about iMachining is that we can use it with bullnose tools, which have a flat bottom and a nose radius. That nose radius is always at a much higher surface velocity, and therefore we can step that across and work it. And as we're working with slope surfaces, we can enter a scallop calculation that we want, and the system will automatically manage the step overs based on the inclination angle of the surface to give us a consistent staircase height all the way across the entire part. So it's a very good way to run, and it's a lot more effective than doing roughing with a ball nose.
Okay, I read recently that you may provide postless demo versions. Is this true?
That we may provide what type of demo versions?
Postless.
Postless. Interesting. I am not sure what a postless demo version would be worth, because if you can't post out, then what do you do with it? But
if the person who asked that wants to write back in with more clarifications, feel free. We still have some time.
I think he's meaning if he was a trial customer.
Yeah, I was going to say, I think he's looking for the ability to do a trial. And one of the things that we will do is, depending on circumstances and such, we will do trials with people. There are some things that we need to make sure that they're aware of and willing to commit to before we will do a live cutting trial with them. Of course, that can be dangerous. We're on a computer thousands of miles away maybe, and we want to make sure everything's running right on their machine. But yeah, call us. We'll talk to you about it, and if we can set something up with you and get all the ducks lined up, we'll do a live cut with you.
All right. How can the tool last so long when you're running it so hard?
Well, that's the thing about the physics-based calculations. Because of the way that we're doing this, CNA, let me step back a second. In a traditional toolpath pattern, when you overload the tool, let me use my hands to kind of show this, the flute of the tool as it's traveling around, when it gets into an overload condition, the force vector is actually putting tensile force on the edge of that flute. Because of the way we do our calculations, the force vector is always tangent to the curvature and follows in that manner as the angle is ranging. And so because of that, that very delicate area here of the sharp flute is only ever seeing compressive force. It's not ever seeing tensile force. It's going to cause it to microfracture. And so even though we're at a much higher performance level, the tool is actually running in an extremely comfortable condition because it's never seeing a linear force. It's always rotary torsional force.
All right. I have one more question here. So if anybody else has anything they want to ask,
I've got one for Ken, and or maybe something to kind of bring up is, Ken is going into great detail of all the science of the cutting angle and everything that's going on behind the scenes. But the really cool feature of this, guys, is all we have to do is grab a material, tell it what machine we're running on and what tool, and it provides everything for you guys. So it really makes machining fun again for us machinists. So I just wanted to throw that out there because, like I said, we're getting into the deep science of it. But just keep in mind, everyone that's listening here, very simple, easy to use. All we had to need is the material, the end mill size, and the machine we're running on. And like Ken was talking about, I couldn't get off mute in time with the aggressive bar, but think if you're running with double-sided sticky tape or we're running that baby in a Kurt vise, and you're golden. So.
Yep, absolutely. Very well said. Very well said.
Thanks, Kevin. Our last question actually kind of relates to that. So what is the difference between 1 and 8 on the level slider?
It's the level of performance. What we do is from level 1 to level 5, the cutting edge velocity, the chip thickness, and the minimum maximum cutting angles are elevating from 1 to 2, 2 to 3, 3 to 4, 4 to 5. From 5 to 6 to 7 to 8, only the feeds and speeds are elevating, the velocity and the chip thickness, if you will. The cutting angle remains constant at that point. So that, what we call the machining level slider, gives us the ability to be extremely effective in deciding how aggressive we want to run our performance. And like Kevin said, very simple. Set it and run it.
Right.
Okay, we actually got a couple more questions in here, so let's try and knock these out. Do we add the materials individually, or do you have a tool and machine library?
We have a library that comes with it, and we also have the ability to add to it or modify and identify your own settings.
All right, we're down to one more question again. Do I get a training guide of iMachining if I buy the package?
Yes, and we recommend the training. In fact, like I said, I'm headed for the airport here shortly to go out to Phoenix and do some training for somebody. So we advise you to get training. There is a lot of training documentation, and there are a lot of videos available on our website for it. Bottom line is, yes, you definitely get some training with it.
Yeah, and to answer that just a little bit further in depth, all of our support guys, if you buy the iMachining package, one of our support guys is going to work with you hand in hand to get your database, everything polished 100% for you to make sure that you got a good grasp of what we're trying to introduce to you.
Absolutely. Service is number one at SolidCAM.
Yep.
All right, I think that's all we have for today. I want to thank Ken and SolidCAM for making this webinar possible, and thank you to everyone for listening in. You should receive an email with a link to the recording soon. Thank you for your time and enjoy the rest of your day.
Thank you, everybody. Do enjoy your day.